Years after the Higgs boson particle was discovered, the world's largest research experiment is still trying to unlock the mysteries of our universe. CERN, located on the outskirts of Geneva, simulates the aftermath of the Big Bang by launching protons into one another at near light speed. Despite the physics community's excitement when the Higgs boson was discovered in 2012, and the general public's relief that the experiment did not suck the entire planet into a gaping vortex, there is still much to learn. What have CERN scientists recently discovered? In this video, we'll take a look at everything you need to know about the CERN's latest disturbing discovery. CERN researchers made headlines around the world a decade ago when they discovered the Higgs boson, a long-sought particle that gives all other particles in the universe mass. What else is there to learn? According to optimistic scientists, almost everything. When the CERN collider was first turned on in 2010, the entire universe was up for grabs. The largest and most powerful machine ever built was built to search for the Higgs boson. The Standard Model, a system of equations that describes everything scientists have been able to measure about the subatomic realm, is built around that particle. However, the Standard Model does not address some larger questions about the universe. What is the universe's origin? Why is it made of matter rather than antimatter? What is the dark matter that pervades the universe? What gives the Higgs particle its mass? When the Large Collider was first turned on in 2010, physicists were looking for answers. Except for the Higgs, no new particles were discovered that could explain the nature of dark matter. Unfortunately, the Standard Model was unaffected. 10 years ago, ecstatic physicists working on the world's most powerful science experiment, the Large Hadron Collider at CERN, announced the discovery of the Higgs boson, a particle whose existence had been predicted in 1964. The Higgs boson was the missing piece of the Standard Model for particle physicists. Victoria Martin, a professor of particle physics at the University of Edinburgh in the United Kingdom, told the sources, although the Large Hadron Collider's mission is broad, finding the Higgs boson was its top priority when it first went online in 2010. Within 2 years of starting operations, the LHC's two key experiments, ATLAS and CMS, discovered the Higgs boson. "We were not expecting to see the Higgs boson so quickly," said CERN Director General Fabiola Giannotti at a preview press conference on June 30. The LHC's superior computing infrastructure was applied to experiments that performed better than their design specifications, a testament to the many years of hard work put into building the LHC, she said. The discovery of the Higgs boson transformed particle physics, opening previously closed doors. Particle physics has changed more in the last 10 years than it has in the previous 30 years, said Jian Judas, head of CERN's Theoretical Physics Department, during the event. The Higgs boson is significant because it carries the force of an energy field known as the Higgs field, much like a photon does for the electromagnetic field. Martin stated, "The field is more fundamental than the particles. It extends all the way through space and time. The interaction of certain particles with the Higgs boson, which represents the Higgs field, is what causes those particles to have mass. Consider the Higgs field to be a kind of cosmic treacle that slows down some particles more than others. Less massive particles pass through the Higgs field relatively easily, allowing them to escape at the speed of light. Consider electrons, which have a very small mass, or photons, which have no mass at all. Other particles are the most massive because wading through the cosmic treacle of the Higgs field slows them down and gives them more mass. Scientists believe that, like these particles, the Higgs boson gets its mass from interacting with itself, though they have yet to observe the process. And LHC measurements show that the Higgs boson has a high mass as well, 125 billion electron volts, which is about 125 times more massive than one of an atom's positively charged protons. Only one known fundamental particle is more massive. The discovery and measurement of the Higgs boson was only the beginning. We've spent the last 10 years testing the Higgs boson because, while discovering it was exciting, the Standard Model also tells us a lot about how the Higgs boson should behave, Martin explained. For one thing, the quantum spin of the Higgs boson, or lack thereof, may provide insight into why our universe exists at all. Except for the Higgs boson, every known particle has a quantum spin. This anomaly was predicted by the Standard Model of particle physics, so it is not surprising, but scientists, including Martin and her research team, have continued to try to measure the spin of the Higgs boson as a way to test the Standard Model. So far, no evidence of spin has been discovered. Because of the nature of the Higgs field, the Higgs boson has no spin while every other known particle does. The Higgs field has no obvious source, unlike gravitational and electromagnetic fields, which have obvious sources such as an object's mass or an electric current passing through magnetic fields. It's just there, a non-localized part of the universe that pervades everything. As a result, the field is coupled to the vacuum, the very fabric of space-time, and thus shares the vacuum's properties. Because the vacuum has no quantum spin, neither does the Higgs boson. The vacuum, however, is not inert because of quantum fluctuations. Particles come and go, raising the energy level of the vacuum above its lowest possible state. The thing about energy levels is that any object, whether it's a person in a gravitational field, an electron orbiting an atomic nucleus, or the vacuum, prefers to be at the lowest possible energy level. However, our universe is not. The shape of what scientists call the Higgs field's energy potential is what keeps the universe from succumbing to the inevitable urge to reduce energy levels. A graph of this energy potential would look like a mountain in the center, flanked by two valleys on either side. The vacuum's energy level would be in one of those valleys, but physicists believe that on either side of those hills are deeper valleys representing even lower energy states. And the Higgs boson's mass measurement backs up this theory. The particle is so massive that there's room for the Higgs field to decay to a lower energy level one day. As a result, physicists refer to our vacuum as a false vacuum because it wants to decay to a lower energy, a truer vacuum. The valleys and hills of the Higgs field's energy potential keep our universe in this false vacuum long enough to form planets, stars, and galaxies. However, the false vacuum is inherently unstable and will decay over aeons upon aeons of time. Perhaps quantum energy fluctuations will allow the false vacuum to climb over those hills and roll down the slope on the other side, or perhaps the strange phenomenon of quantum tunneling will allow it to drill through the energy barrier's hill. Whatever happens, the decay of the false vacuum would spread outward in a wave moving at the speed of light, destroying everything and replacing it with a true vacuum. Because it is only the Higgs field that prevents vacuum decay, we must thank the Higgs field for our current universe. In addition to the Higgs boson spin, scientists have spent the last decade attempting to determine its lifetime. The Higgs boson's existence is fleeting. The standard model predicts that a Higgs boson lives for only 10 to 22 seconds before disintegrating into more subatomic particles. However, this calculation has yet to be experimentally validated. It all happens so fast. Martin said, physicists hope that the next operational phase of the LHC, Run 3, which begins on July 5, will serve as the much-desired stopwatch. We hope that we will be able to measure how long the Higgs boson lives in an indirect way. Martin said, if we can measure the lifetime, we will have more information about what particles the Higgs boson decays into. Understanding how the Higgs boson breaks apart into other particles in turn could reveal previously unknown subatomic particles, possibly including particles of mysterious dark matter. The Higgs boson, on the other hand, continues to keep its secrets hidden. Moving beyond the standard model, rather than breaking the rules and destroying physics, is required to explain phenomena that do not fit, such as dark matter, or to open doors into new physics, such as supersymmetry. That is why, after 4 years of upgrades, the LHC will tackle the mysteries of the Higgs boson once more. And with that being said, it's time to end our video. Subscribe to the channel for more amazing videos like this. We'll see you with another interesting video.